Here is something that should not be true, and yet it is. The same physics that forbids anything from traveling faster than light is the physics that contains the warp drive. Both ideas come from Einstein. Both are written in the same language. One is taught as an unbreakable law, the other dismissed as a daydream, and the longer you sit with the line between them, the thinner it starts to look. Tonight, we are going to walk all the way around that line until you can see exactly where it bends. So make yourself comfortable and let the world go quiet, because by the end, you may never think about the word impossible the same way again. The number that came from a real equation. There is a number that has been quietly sitting inside a real physics paper for more than 30 years, and almost nobody outside a small circle of theorists has ever stopped to look at it properly. The number is 10, as in 10 times the speed of light. Not a figure pulled from a film script, not a line of dialogue handed to an actor on a glowing bridge, but a worked example written into a peer-reviewed paper by a working physicist, published in a respectable journal, and never quite refuted. If that sentence makes something tighten in your chest, good. Hold on to that feeling, because we are going to spend the next couple of hours slowly turning it over from every angle, and by the end, you will understand exactly what that 10 means, where it came from, and why a small group of scientists in the last few years has started arguing about it all over again. The paper was written in 1994 by a physicist named Miguel Alcubierre, and it carried a title that sounds almost cheeky for a serious journal. He called it The Warp Drive, Hyperfast Travel Within General Relativity. That last phrase is the one that matters. Within general relativity, he was not proposing to break Einstein's rules. He was proposing to use them. And the example he chose to illustrate his idea was a ship that travels to a distant star and comes home again at an effective speed of about 10 times the speed of light. That 10 was never a ceiling. It was just the number he picked to make the point. The math, as we will see, would have let him write 100 or 1,000 just as easily. So here is the paradox we are going to live inside tonight, and I want you to feel how strange it is. The very same physics that tells us, with absolute confidence, that nothing can travel faster than light is the same physics that contains the warp drive. Both ideas come from Einstein. Both are written in the same language, the language of curved space-time. One of them is taught in every introductory course as an unbreakable law. The other is treated as a curiosity, a piece of mathematical poetry that could never be built. And the longer you sit with the question of why one is law and the other is a curiosity, the more you start to suspect that the line between them is thinner than anyone wants to admit. The trick at the center of all this, the single idea that everything else hangs from, is so simple that it sounds like a cheat when you first hear it. You do not move the ship through space quickly. You move space. That distinction is going to do an enormous amount of work for us tonight. So let me say it again in a slightly different way. Imagine the difference between running across a room and standing perfectly still on a moving walkway while the room slides past you. In one case, you are doing the moving. In the other, the floor is. The warp drive is the second case, scaled up to the size of the cosmos, with space-time itself playing the role of the walkway. And it turns out the universe has very strong opinions about how fast you can run, and almost no opinions at all about how fast the floor can move. What makes this the right night to talk about it is that the story did not end in 1994. For nearly 30 years, the warp drive sat in a drawer, admired as elegant math and dismissed as hopeless engineering, because it seemed to demand an ingredient we have barely ever produced, and could never produce in the quantities required. And then, starting around 2021 and continuing right up through 2025, a handful of physicists pulled the file back out. They published new papers with new geometries, and they began chipping away at the one objection that had kept the idea locked up. The energy bill started shrinking, the math started looking more physical, and the question in our title stopped being a joke and started being something people argue about at conferences. I want to be honest with you about where we are going, because this is not a channel that sells you a fairy tale and leaves you there. The answer to the question, have we just found a way to travel 10 times faster than light, is more interesting than a simple yes or no, and it is more interesting precisely because it refuses to be either. On paper, in fresh and serious mathematics, the door looks less bolted than it did 10 years ago. In a laboratory, we are not even within a galaxy's reach of building the thing. And between those two facts lies one of the most beautiful arguments in modern physics, an argument about what the word possible even means. It helps, before we go any further, to understand why this particular dream refuses to die when so many others have quietly faded. Humans have wanted to cross great distances for as long as there have been humans, and for most of our history, the limit was simply how fast a thing could be pushed. A faster horse, a better sail, a stronger engine, a bigger rocket. Each time, the answer to going farther was going faster, and each time it worked, because nothing in our daily experience suggested there was a ceiling. You could always, in principle, build a faster thing. The speed of light shattered that assumption permanently. For the first time, the universe told us that no amount of cleverness with engines would ever get us where we wanted to go, because the destinations are so far away that even light, the fastest thing there is, takes years and centuries and millennia to reach them. The warp drive matters because it is the one idea that refuses to accept that the engine is the answer at all. It changes the question entirely, from how do we push the ship faster to how do we move the road beneath it, and that change of question is what keeps serious people awake at night 3 decades after Alcubierre first wrote it down. To get there, we have to do this slowly and in order, the way you would walk around a strange and enormous machine in a dark room, running your hand along its edges until the shape of it comes clear. First, we are going to respect the wall, the reason every physicist will tell you that faster-than-light travel is forbidden, because that wall is one of the best tested ideas in all of science, and we are not going to wave it away. Then we are going to find the crack in the wall, the loophole that the universe itself uses every single night across the whole sky. Then we are going to look at the machine that tries to drive through that crack, the warp drive, and we are going to climb inside it and ask what the journey would actually feel like. And only then, once you understand the idea in your bones, will we meet the physicists who reopen the file and weigh what they have really found. So, settle in, get comfortable. This is going to be a long, calm walk through one of the strangest ideas that real science has ever taken seriously. And the first thing we need to understand, before we can understand the loophole, is the wall itself. Because to appreciate why moving space is such a clever trick, you first have to understand just how completely the universe forbids the obvious thing, the thing every child assumes you could do if you just had a fast enough rocket. You cannot. And the reason you cannot is one of the most thoroughly proven facts we have ever discovered is less than break time equals 1s, is greater than number. Why everyone is sure it's impossible. The speed of light is not a fast speed, it is the speed. There is a difference, and the difference is the whole reason the warp drive is interesting. Light travels at about 300,000 kilometers every second, and to give that number a shape you can hold, consider this. A beam of light leaving the surface of the moon reaches your eye on Earth in a little over 1 1/3 seconds. A beam leaving the sun takes about 8 minutes and 20 seconds to arrive, which means that the sunlight warming your face right now left its source before you sat down. That is the fastest anything in the universe is permitted to move, and the word permitted is doing something very specific there. It is not that we have not built a fast enough engine yet. It is that the universe has written a rule, and the rule does not bend for engineering. The rule comes from special relativity, which Einstein published in 1905, and the cleanest way to feel why the rule exists is to imagine trying to break it. Suppose you have a spaceship and an infinite supply of fuel, and you decide you are simply going to keep accelerating until you pass light speed. At first, everything behaves the way your intuition expects. You burn fuel, you go faster, the stars ahead shift their colors. But as you climb toward the speed of light, something begins to go wrong with the bargain. Each additional sliver of speed costs more energy than the last, not a little more, dramatically more. The curve that relates your energy to your speed begins to bend upward, and, as you approach light speed, it bends straight up toward infinity. What that means in plain language is that the last tiny fraction of speed, the final step that would carry you across the line, costs more energy than all the speed you gained before it combined. And the step after that costs more still. To actually reach the speed of light, a ship with any mass at all would need an infinite amount of energy, and there is not an infinite amount of energy in the universe to give it. This is not a practical limit that a better reactor could overcome. It is a wall built into the structure of reality, and the closer you get to it, the higher it rises in front of you, as if the universe itself were leaning its weight against the door. It is worth feeling just how cruel that arithmetic is, because the numbers do not climb gently. Getting a ship to half the speed of light is hard but imaginable. Getting it to 90% is far harder. Getting it to 99% harder still. And from there, each additional 9, 99.9, 99.99 costs more than everything that came before, the energy bill doubling and redoubling toward a sum no civilization could ever pay. You never actually arrive at the wall. You only watch it recede in front of you, always the same impossible distance away, no matter how much you spend, like a horizon that retreats with every step you take toward it. The speed of light is not a finish line you might cross with enough effort. It is an asymptote, a value you can approach forever and touch never. And that mathematical shape is the universe's quietest and most absolute way of saying no. And here is the part that makes the limit feel less like physics and more like a kind of law of fate. It applies to everything with mass, equally, without exception, from a spaceship to a single electron to a thought travelling as a signal down a nerve. There is no special material, no clever trick of shape or spin or arrangement that lets any massive thing slip past it. The only objects that travel at light speed are the ones that have no mass at all, like light itself, and they have no choice in the matter, no ability to carry a passenger or a message of their own choosing. The door is not just locked, it is the kind of locked that has no keyhole, because there was never meant to be a key. The universe does not stop there. It has other ways of protecting the speed limit, and they are stranger than the energy wall. As you move faster, your experience of time itself begins to change relative to the people you left behind. Moving clocks run slow. This is not an illusion or a trick of measurement. A clock carried at high speed genuinely ticks fewer times than a clock left at rest, and the faster it moves, the more it lags. Alongside that, moving objects shrink along their direction of travel. A ruler flying past you at enormous speed is genuinely shorter than the same ruler sitting still. Space and time themselves stretch and compress to keep light speed constant for everyone, no matter how fast they are moving. The universe would rather warp time and shrink rulers than let anything outrun light. If this sounds like abstract theory that could be wrong, I want to take that worry away from you, because the speed limit is one of the most relentlessly tested ideas in all of science, and it passes every time. In particle accelerators, we push protons to more than 99.9% of light speed, and we watch them get heavier and harder to push exactly as relativity predicts, never quite reaching the line, no matter how much energy we pour in. The satellites that run the positioning system in your phone carry atomic clocks that tick at a slightly different rate than clocks on the ground, and engineers have to correct for that difference every single day, or your navigation would drift by kilometers. Particles called muons, created high in the atmosphere by cosmic rays, should decay long before they reach the ground, and yet they arrive, because they are moving so fast that their internal clocks run slow and their journey takes less time from their point of view. Everywhere we look, at every scale we can probe, the limit holds. I want to dwell for a moment on why the speed limit takes this particular form, because the reason is more elegant than the rule itself. The speed of light is not really the speed of light at all. That is a kind of accident of history, the fact that we discovered it by studying light first. It is better understood as the speed of cause and effect, the maximum rate at which any influence can travel from one place to another, the speed at which the universe updates itself. Light happens to travel at that speed because light is massless, and anything massless is obliged to move at exactly that rate, no faster and no slower. But the limit would exist even in a universe with no light in it at all, because it is built into the geometry of space and time themselves, into the way the two are woven together. When we say nothing can exceed the speed of light, what we are really saying is that nothing can outrun the universe's own ability to connect a cause to its effect. And that reframing is going to matter enormously later, because it explains why faster-than-light travel is so dangerous to the order of reality, and why physicists guard this limit so fiercely. There is something almost poetic in how the universe enforces the rule too, because it does not simply forbid the forbidden speed. It reshapes space and time to make the limit unreachable from any direction. As you go faster, your time slows and your length shrinks, and these are not punishments bolted on afterward. They are the universe rearranging your experience so that, from your own point of view, light still races away from you at exactly the same speed it always did, no matter how fast you yourself are traveling. You can never catch light, because every time you speed up, the universe quietly adjusts your clock and your ruler so that light keeps its lead. It is the most patient and inescapable rule in all of physics, and it is the wall we will spend the rest of the night learning to walk around rather than through. This is why, when you ask a physicist whether anything can travel faster than light, the answer comes back not as an opinion, but as something closer to a reflex, the way you would answer if someone asked whether water could flow uphill on its own. Nothing goes faster than light. It is taught as a law, felt as a law, and tested as a law, and for the kind of travel everyone first imagines, the kind where you point a ship at a star and simply go faster and faster, it is completely and permanently true. You will never thrust your way past light. The wall is real, the wall is enormous, and the wall is not going anywhere. And yet, I want you to notice the exact words I have been careful to use, because everything that follows depends on them. The limit forbids moving through space faster than light. Through space. That little word, through, is not decoration. It is the precise statement of the law, and it contains, hidden in plain sight, the crack that the warp drive will eventually slip through. Special relativity is a rule about how things move through the fabric of space-time. It says nothing, not one word, about how fast that fabric itself is allowed to move. And as we are about to see, the universe takes full advantage of that silence, on a scale so enormous that the warp drive starts to look less like a fantasy and more like an imitation of something the cosmos has been doing since the very first instant of time. Is less than break time equals 1s, is greater than number. The universe already cheats. Here is the sentence that changes everything, and I want to deliver it plainly so it has room to land. The speed limit governs how things move through space, but general relativity, Einstein's later and grander theory, treats space itself as a living thing that can stretch, shrink, and flow. Space is not an empty stage on which events happen. It is a participant. It bends around mass. It ripples when black holes collide. And most importantly for us tonight, it can grow. And when space grows, the things sitting in it can be carried apart at any speed at all, including speeds far beyond light, without a single one of them breaking the rule, because none of them is moving through their own local patch of space faster than light. They are just sitting still while the space between them swells. The clearest place to see this is the expanding universe, which is not a theory anymore, but a measured fact, established almost a century ago and confirmed thousands of times since. The galaxies are rushing apart from one another, and the natural first guess is that they are flying outward through space, like fragments from an explosion. But that is not what is happening. The galaxies are, for the most part, sitting more or less still in their own neighborhoods. It is the space between them that is expanding, new distance appearing everywhere all at once, so that two galaxies find themselves farther apart each year, not because either one traveled, but because the gap itself grew. Imagine two dots drawn on the surface of a balloon. As you inflate it, the dots move apart, but neither dot is crawling across the rubber. The rubber itself is stretching. And notice the crucial detail in that picture, the one that breaks the speed limit's grip. An ant standing on either dot would measure no motion at all in its own immediate neighborhood. It could check its speed against the rubber directly beneath its feet and find it sitting perfectly still. The growing distance to the other dot is not something either ant is doing. It is something the space between them is doing, and the speed limit, remember, only ever governed motion through space, never the stretching of space itself. This is the single idea that unlocks everything, so I want to state it in the bluntest possible terms before we go on. There are two completely different ways for the gap between two things to grow. One way is for the things to move apart through space, and that way is governed by the speed limit, capped forever at the speed of light. The other way is for new space to appear between them, and that way has no limit at all, because nothing is moving through anything. The universe uses the second way constantly, on the largest scales, and it is the only way anyone has ever found, even in principle, to put distance between 2 points faster than light could cross it. Every serious idea about beating the speed of light, the warp drive included, is ultimately an attempt to harness that second way, to grow or shrink space on purpose rather than to race through it. Now follow that idea to where it gets genuinely shocking. If space is expanding everywhere, then the farther apart two galaxies are, the more expanding space lies between them, and the faster they recede from each other. Push that far enough, and you reach galaxies so distant that the space between us and them is growing faster than light can cross it. Those galaxies are receding from us faster than the speed of light right now, tonight, as you lie there listening. And not a single law of physics is being broken, because not one of those galaxies is moving through its own space faster than light. The recession is built entirely from the stretching of the space in between. The universe is doing the forbidden thing, casually, constantly, on the largest scale there is. If that were the only example, it would be enough to make the point. But the universe did something even more extreme right at the beginning, in the first unimaginably small fraction of a second after the Big Bang. According to the theory of cosmic inflation, proposed in 1981, the infant universe went through a burst of expansion so violent that it ballooned in size by a factor with 26 zeros after it, all in a span of time so short that writing it out requires a decimal point followed by more than 30 zeros before you reach a single one. During that instant, the fabric of space expanded outward far, far faster than light, dragging the seeds of every future galaxy along with it. The patterns we see today in the oldest light in the sky, the faint glow left over from the early universe, are the fingerprints of that impossibly fast expansion frozen in place, and still readable billions of years later. When astronomers map that ancient light and find it almost perfectly smooth across the entire sky, they are looking at direct evidence that regions now separated by more than the speed of light could allow were once in contact, then flung apart faster than any signal could follow. We do not infer the cosmic loophole from theory alone. We photograph its aftermath. The largest, fastest motion in the entire history of existence was not anything moving through space. It was space itself, unfurling. The scale of what this leaves behind is almost impossible to fit inside a human mind, so let me anchor it with one comparison. The observable universe, the sphere of everything we can in principle see, is about 93 billion light-years across. But the universe is only about 13.8 billion years old. If nothing could ever outrun light, the farthest we should be able to see in any direction is around 13.8 billion light-years, and the whole observable sphere should be roughly twice that across. Instead, it is more than 3 times larger than that simple limit allows. The only way to explain the gap is that space has been expanding the whole time, carrying distant regions away faster than light could ever have travelled between them. The proof that the universe cheats the speed limit is written across the entire sky, in the very size of the cosmos. There is a consequence of all this expansion that is worth sitting with, because it makes the cosmic loophole feel personal rather than abstract. Right now, in the sky above you, there are galaxies whose light is reaching your eyes tonight, but which have, in the time that light spent travelling, been carried so far away by the expansion of space that we could never reach them, not even if we left this instant at the speed of light. They have crossed beyond what cosmologists call the cosmic event horizon, a boundary set not by how fast we can travel, but by how fast space is growing. Those galaxies are still out there, still real, still full of stars and perhaps worlds, and they are gone to us forever, not because they moved through space too fast, but because the space between us swelled faster than light could ever cross it. The universe is quietly, constantly carrying parts of itself out of our reach by exactly the trick the warp drive hopes to harness. The loophole is not a curiosity at the edge of theory. It is actively rearranging what is and is not reachable every second on the largest scale there is. And the truly maddening thing, the detail that turns this from a lecture into an obsession, is that the universe does it so casually. There is no machine doing the expanding. There is no engine, no fuel, no exotic substance being consumed. Space simply expands because that is what space does, woven into the basic behavior of the cosmos from the first instant. Nature performs the impossible thing for free, without effort, while we sit here calculating that to do the same trick in a region the size of a ship would cost us the energy of a planet. The universe is not showing off. It is simply built that way. And the warp drive is, at its core, an act of imitation, an attempt to copy by brute engineering a thing the cosmos does as easily as breathing. So sit with the realization for a moment, because it reframes our whole question. The thing that special relativity calls impossible, the thing that feels like the most unbreakable law in physics, the universe has already done, routinely, on the grandest stage imaginable. It did it in the first instant of time, and it is doing it right now at the edges of what we can see. The catch, the thing that keeps this from being a free ticket to the stars, is that the universe does it everywhere, all at once, gently and on enormous scales, not in a tidy little bubble that you could climb inside and steer toward a particular destination. Nature moves space, but it does not pack a suitcase and choose where to go. And that is exactly the question the warp drive dares to ask. If space can move faster than light on its own, with no law broken and no rule bent, could we make a small, controlled patch of space do the same thing on purpose? Could we squeeze the space in front of a ship and stretch the space behind it, building a little travelling region of expansion and contraction, A bubble that carries its passenger along the way the early universe carried the seeds of galaxies? The whole game, the entire project that has occupied physicists from Alcubierre in 1994 to the authors publishing in 2025, is the attempt to do locally, by engineering, what the cosmos does for free across the whole sky. And to see how that could even be imagined, we have to look at the machine itself. Is less than break time equals 1s, is greater than, number, surfing. A wave you make yourself. Picture a bubble. Not a soap bubble, but a region of perfectly ordinary, flat, well-behaved space. Exactly the kind of space you are sitting in right now, with a ship resting calmly inside it. Around that bubble, Alcubierre imagined a wall, and the wall is where all the magic lives. In front of the bubble, in the direction the ship wants to travel, space is being contracted, squeezed together so that the distance to the destination shrinks. Behind the bubble, space is being expanded, stretched out so that the distance already covered grows. The bubble itself, the calm, flat region in the middle with the ship inside, gets carried forward on the seam between that contraction and that expansion, the way a small boat is carried forward on the front face of a wave. The surfer is the metaphor everyone reaches for, and it is a good one as long as you push it to its proper conclusion. A surfer riding a wave is not swimming. If you measured how fast the surfer's arms and legs were moving through the water, you would find they are barely moving at all. The wave is doing the work, lifting the surfer and carrying them toward the shore at the speed of the wave, not the speed of the swimmer. Now make the wave out of space-time instead of water, and let the surfer build their own wave continuously beneath themselves as they go, and you have the essential picture of the warp drive. The ship is not moving through space. The wave of warped space is moving, and the ship rides along on it, sitting still in its own little pocket of flatness. Look more closely at the front wall, because that is where the real speed comes from. Space ahead of the ship is being compressed, and compressed space means the destination is, in a very literal sense, closer than it was. The 4 light years to the nearest star are not crossed so much as folded shorter. Imagine a long sheet of fabric with your destination marked at the far end, and now imagine gathering the fabric in front of you into tight pleats so that the far end slides toward you without you taking a single step. That is the front wall of the bubble. It does not carry you forward by pushing. It brings the destination to you by shrinking the space in between. This is the single hardest part of the idea to hold in your head, so let me come at it from another direction, because once it clicks, it stays clicked. Think of distance not as a fixed property of the universe, but as something that can be more or less, depending on how space is arranged. In ordinary flat space, the distance between here and a star is whatever it is, and the only way to cover it is to travel the whole length. But space is not obliged to stay flat. Near a heavy object it curves, and distances measured through that curved region are different from what you would expect. The warp drive takes that fact and weaponizes it. By contracting the space directly ahead, it makes the path shorter, genuinely shorter, not as a trick of perspective, but as a real reshaping of how much distance lies between the ship and its goal. You are not cheating the distance by going fast. You are reducing the distance itself, melting it down in front of you and pouring it out behind. There is a beautiful symmetry in how the two walls cooperate, and it is worth admiring before we move on. The front wall pulls the destination closer by squeezing space, and the rear wall pushes the ship onward by stretching space, and the flat bubble simply floats on the boundary where squeeze meets stretch, never feeling either one. It is a little like standing on the exact crest of a wave, where the water is rising in front and falling behind, perfectly balanced at the still point in the middle. The crew sits in that still point, and the still point itself races across the cosmos. Everything dramatic happens at the edges of the bubble, in the violently curved walls, while the center remains as calm as a quiet room. The genius of Alcubierre's design is that it puts the passenger in the one place where nothing strange is happening, and lets the strangeness happen all around them. The rear wall does the opposite, and together the two walls make the bubble move. Behind the ship, space is expanding, new distance constantly being created, and that expansion presses against the back of the bubble and drives it forward, the way the early universe's expansion drove galaxies apart. So you have contraction pulling the destination closer in front, and expansion pushing the bubble onward from behind, and trapped between them, riding the seam, is the flat little region where the ship and its crew sit in complete calm. Nothing inside the bubble ever moves quickly. Everything outside it is rearranged at speed. Now we arrive at the claim that sounds impossible until you have understood everything we just built, and I want to state it as plainly as I can. Inside the bubble, the ship never breaks the local speed limit. A passenger floating in that flat pocket of space could shine a flashlight forward and watch the beam pull away from them at the normal speed of light, exactly as relativity demands, because locally, in their immediate neighborhood, nothing strange is happening at all. And yet the bubble as a whole, carried on its wave of contracting and expanding space, can travel between 2 points faster than a beam of light sent through ordinary, undisturbed space. The ship obeys every rule in its own little region, while the region itself outruns light. The speed limit is never violated, because the speed limit was only ever about moving through space, and the ship is not moving through space. The space is moving. This is the moment to come back to the number in our title, because now you can see what it really means. In Alcubierre's mathematics, the speed of the bubble is a free parameter, which is a physicist's way of saying it is a dial you can set to whatever you like. He set it to about 10 times the speed of light for his example, but there was nothing special about 10. He could have written 100. He could have written 1000. The equations do not contain any built-in ceiling because there is no wall of infinite energy to climb. You are not accelerating a massive object through space toward light speed. You are setting how fast a wave of warped space rolls forward, and waves of warped space, as the expanding universe proves, have no posted speed limit. So, the real question, the one that has occupied every physicist who has touched this idea, was never why 10 times light speed. The 10 could just as easily be 1,000. The real question is whether you can build the wave at all. Can you actually source the geometry? Can you make matter and energy arrange themselves into that specific pattern of contraction in front and expansion behind, and do it without something going horribly wrong? That is the question, and it is a far harder and far more interesting question than the simple matter of how big a number you write on the dial. What I find most remarkable about all of this, and what I want you to carry forward, is that none of it rewrites Einstein. The warp drive is not a rebellion against general relativity. It is a solution of general relativity, a perfectly valid configuration of curved spacetime that you can find by working through the same equations that describe black holes and orbiting planets and the bending of starlight around the Sunday. Alcubierre did not break the rules to get his result. He read the rules more carefully than anyone had before, and noticed that they permitted something nobody had thought to ask for. A working physicist published it in a serious journal, and rather than being laughed out of the field, it was taken seriously, studied, refined, and argued about for the next 3 decades. But noticing that the universe permits a thing is not the same as knowing what that thing would be like, and there is a feature of life inside the bubble so strange and so quiet that it changes the whole emotional character of the idea. If the ship truly sits still while the galaxy slides past it, if there is no acceleration and no engine roar and no sense of speed at all, then what, exactly, would the journey feel like from the inside? The answer is one of the eeriest things in this entire story. Is less than break time equals 1s, is greater than number inside the bubble. Imagine yourself as the passenger, floating in the flat pocket of space at the center of the bubble, and the first thing you would notice is that you feel nothing at all. There is no acceleration. There is no force pressing you back into a seat, no rumble of engines, no sensation of speed. You are weightless, in perfect free fall, drifting as gently as an astronaut in orbit, and this remains true no matter how fast the bubble is traveling. Whether the wave outside is carrying you at 10 times light speed or 1,000 times light speed, your experience inside is identical, because you are not the thing that is moving. The space around you is, and space carries you without a single tug. Contrast that with what it would take to reach these speeds, the ordinary way, by thrust, and you start to see why the warp idea is so seductive. To accelerate a ship to even a fraction of light speed using rockets, the crew would be crushed under enormous forces for months or years, their bodies pressed flat against the back wall, their bones and blood unable to survive the strain of the acceleration required. The faster you want to go by thrust, the harder the universe pushes back on your fragile body. The warp bubble simply removes the problem. There is no acceleration to survive, because the ship never accelerates. It sits still in flat space from the first moment to the last, and the cosmos is rearranged around it. The strangeness goes further, into time itself. When you travel close to light speed by ordinary means, time dilation becomes severe. The famous twin paradox describes one sibling flying off at near light speed and returning to find the stay-at-home twin has aged decades, while the traveler has aged only a few years. The faster you go through space, the more your clock falls out of step with everyone you left behind. But inside the warp bubble, because you are sitting still in flat space, there is little or no time dilation between you and the universe outside. You could travel to a distant star and return barely older than when you left, to a home barely changed, your friends and family having aged at almost the same rate as you. The warp drive does not just beat the speed of light. It beats the cruel arithmetic of relativistic time that would otherwise let you reach the stars only by abandoning everyone you knew. Try to picture the view, because this is where the wonder and the unease meet. You float at a window, perfectly still, your coffee hanging in a sphere in front of you, and outside, the stars do not streak past the way films love to show. Instead, the whole arrangement of the heavens slides and shifts as the bubble reshapes the space around it, and a destination that lies 4 light years away begins to swell into view not over years, but over months, growing from a point of light into a disk, a world, a place, while you sit motionless in your chair. There is no sensation of motion at all. There is only the universe rearranging itself outside the glass, silent and smooth, as though you were not travelling to the star but summoning it toward you. What that view would actually show is itself a subject of debate among the physicists who have modelled it, and the disagreement is part of the strangeness. Light from the stars ahead has to interact with the curved walls of the bubble before it can reach the window, and depending on how the geometry is arranged, the sky in front might appear compressed into a brilliant point, the light of everything ahead squeezed together and shifted in colour, while the sky behind might stretch and dim toward darkness. Some models suggest the view forward would collapse into a single dazzling spot, the rest of the sky going black, so that the crew would travel toward a single point of concentrated light, like moving down a tunnel toward a distant lamp. Whether it would be beautiful or disorienting or simply impossible to interpret, no one can say for certain, because no one has ever sat inside a region of space being reshaped this violently. It is one more way the warp drive remains a thing of equations rather than experience, a journey we can calculate in some detail and yet cannot truly imagine. That stillness is the emotional core of the whole idea, and it is worth pausing on because it is the opposite of how we usually imagine speed. We think of speed as wind and noise and pressure, as the roar of an engine and the blur of the world rushing by. The warp drive offers speed as perfect calm. The drama is entirely on the outside, in the contortions of space at the bubble's walls, while the inside is the most peaceful place imaginable, a quiet room drifting across the galaxy. It is the kind of motion you could sleep through, which, given the nature of this channel, feels almost too fitting. Consider what a single voyage might actually look like from the inside, hour by hour, if everything worked. You would board the ship in orbit around Earth, strap in out of habit rather than necessity, and feel the bubble form around you, not as a jolt, but as a subtle change in the view outside, the stars beginning their slow rearrangement. There would be no countdown sensation of acceleration, no being pressed back, no blur. You might unbuckle within minutes and float to the window, and over the following days and weeks you would watch a particular point of light ahead of you brighten and grow, while the sun behind you dwindled to just another star, and then to nothing remarkable at all. You could read, sleep, eat, talk, the whole time feeling utterly stationary, as though the ship were parked and the universe were on a conveyor belt being fed past your window. The most extraordinary journey a human being could ever take would feel, from the inside, like the most boring, and there is something almost funny about that crossing light years might be less physically dramatic than a roller coaster. That very ordinariness of the experience is part of what makes physicists take the idea seriously rather than dismissing it as obvious fantasy. A scheme that required the human body to survive impossible forces would be ruled out on biology alone, no matter what the equations said. But the warp drive sidesteps biology entirely. It asks nothing of the passenger's body, because the passenger's body is never accelerated, never stressed, never subjected to anything worse than the gentle weightlessness of freefall. If the drive could be built at all, a child or an elderly person or someone in fragile health could make the crossing as easily as a trained astronaut, because there is nothing to endure. The whole burden of the impossible falls on the machine and on the space-time around it, never on the people inside. That is a strange kind of mercy to find written into an equation, and it is one more reason the idea has such a hold on those who study it. But the calm hides something genuinely disturbing, and I would be doing you a disservice if I let the picture stay entirely gentle. The inside of the bubble, it turns out, is causally cut off from its own leading edge. What that means is that signals, including light, cannot travel from the front wall of the bubble back to the ship while the bubble is moving faster than light. The crew, sealed in their flat pocket, cannot see out ahead of themselves in any useful way. Information from where they are going cannot reach them. They are, in a sense, flying blind, enclosed in a region that has no real-time connection to the space rushing toward it. Spell out what that means for the people on board, and it becomes genuinely unsettling. The crew cannot steer. They cannot look ahead, spot an obstacle, and adjust course, because nothing from ahead can reach them. They cannot decide, halfway through the journey, to slow down or change destination, because the controls that would shape the bubble's leading edge are on the far side of a causal barrier they cannot cross while in flight. The warp ship is less like a car you drive and more like a sealed package that has been addressed, stamped, and dropped into a chute. Once it is moving, the journey is out of the crew's hands entirely. And there is a darker possibility lurking beneath even that, one we will return to in full later, but which I want to plant now, like a seed of disquiet. Some physicists who have studied the bubble closely suspect that its walls might do something terrible to radiation. Particles and light caught up against the front wall could be gathered, concentrated, and slammed with energy, so that when the bubble finally stopped, it might release a lethal burst, frying both the crew and whatever waited at the destination. The peaceful room drifting across the galaxy might also be a bomb that cannot see its own fuse. Whether this is truly fatal or merely a difficulty remains an open question, and it is exactly the kind of question that separates a beautiful equation from a buildable machine. Every one of these strange features, the weightlessness, the gentle time, the blindness, the possible lethal flash, flows from the single idea we started with, the idea that it is space that moves, and not the ship. That one principle generates all the wonder and all the dread together. So if the picture is this gentle and this strange and this nearly perfect, offering the stars without the crushing forces and without the heartbreak of relativistic time, you are right to be asking the obvious question. Why, if it is so beautiful, did this idea get shelved for nearly 30 years? The answer is a single ingredient, and it is the most expensive thing in the universe. Is less than break time equals 1s is greater than number. The catch nobody could pay for. The ingredient that killed the warp drive for 30 years has a name that sounds like a contradiction, and in a way it is. To build the wall of the bubble, to contract space in front and expand it behind in just the right pattern, Alcubierre's mathematics demanded negative energy, not low energy, not a little energy. Negative energy, a quantity less than zero, the energy equivalent of a debt carved into space-time. And negative energy is not the sort of thing you can scoop out of a reactor or refine from fuel. It is one of the rarest and strangest things the universe permits, and for a long time it seemed to slam the door on the whole idea before anyone could even reach for the handle. Let me make negative energy concrete, because it is easy to say the words and hard to feel what they mean. Ordinary matter and ordinary energy always add up to something positive. A rock, a star, a beam of light, the empty vacuum itself, all of these carry energy that is zero or greater. Negative energy means a region where there is, in effect, less than nothing, where the energy dips below the level of empty space. It is the gravitational opposite of normal matter. Where normal mass pulls space inward and bends light toward it, negative energy would push space outward and bend light away. It is exactly this repulsive, outward-pushing quality that the rear wall of the warp bubble needs in order to stretch the space behind the ship. The drive does not just run on strange fuel. It runs on the opposite of fuel. We are not entirely sure that negative energy is impossible, and that is the thin thread the whole field hangs from. There is one place where we have genuinely produced it, in tiny, fleeting amounts, and it is called the Casimir effect. Take two metal plates and bring them extremely close together, closer than the width of a hair, and something subtle happens to the vacuum between them. The empty space between the plates is forced to contain slightly less energy than the truly empty space outside them, which means that, relative to ordinary vacuum, the region between the plates holds a sliver of negative energy. It is real, it has been measured, and it is one of the most beautiful confirmations that the quantum vacuum is not truly empty. But the amounts are unimaginably small, a whisper of negative energy trapped in a gap you would need a microscope to see. The gap between that whisper and what a warp drive needs is so enormous that it is worth trying and failing to picture it, because the failure itself is instructive. The Casimir effect produces an amount of negative energy so tiny that it has taken some of the most sensitive instruments ever built simply to confirm it exists at all. It is the faintest possible trace, a rounding error in the energy of two metal plates. Now imagine needing to gather that effect, that microscopic whisper, and multiply it up until you had the negative energy equivalent of a planet, and then sculpt it into a precise shell around a spacecraft, holding its shape against every tendency of nature to even it back out to zero. It is not a matter of building a bigger version of the Casimir apparatus. It is like noticing that you can lift a single grain of sand with static electricity and concluding that you are nearly ready to lift a mountain range. The principle exists. The scale is a different universe. What makes the negative energy requirement feel less like a price and more like a taunt is that the universe seems to permit negative energy only in these vanishing, fleeting, carefully constrained circumstances. Every time physicists have found a way to produce or borrow a little negative energy, they have also found that nature attaches strict conditions Quantum rules that say you can borrow this much for only this long before you must pay it back, with interest, in ordinary positive energy. It is as though the cosmos allows negative energy to exist in principle, the way a bank allows an overdraft, but polices it so tightly that you can never accumulate enough to do anything useful with it. Whether those rules are an absolute prohibition or merely a very strict accounting is one of the open questions that the whole warp drive revival ultimately depends on. Now set that whisper against what Alcubierre's original drive actually demanded, and you will understand why physicists put the idea in a drawer. The early estimates for the negative energy required to warp a ship-sized bubble came out comparable to the mass of an entire planet, converted completely into energy. Some calculations pushed it higher still, toward the mass of the Sunday. To grasp how absurd that is, remember that we have only ever made negative energy in amounts you could trap between two tiny plates, and the drive was asking for the negative energy equivalent of feeding Jupiter or the Sun into the machine. That is not a fuel tank. That is not even a foreseeable technology. It was a number so large that it functioned as a flat refusal, the universe saying, "You may have noticed the loophole, but you will never afford the toll." For a while, it looked completely hopeless, and then a physicist named Chris van den Broek did something in 1999 that mattered more than its immediate result. He looked at the shape of the bubble and asked whether it had to be so large and so demanding, and he found that by reshaping the geometry, by giving the bubble a tiny neck, a microscopically small opening that flared into a larger interior, you could slash the negative energy requirement by an enormous factor. The number dropped from something like the mass of a planet to something far, far smaller. It was still wildly beyond anything we could produce, but the point was not the new number. The point was that the number moved. The energy requirement was not a fixed law of nature. It depended on the shape of the bubble, and shapes can be optimized. That single realization changed the character of the problem in a way that is easy to undersell. So let me be clear about why it mattered. There is an enormous difference in physics between something that is infinitely impossible and something that is merely absurdly expensive. Infinitely impossible means stop, go home, the door is welded shut. Absurdly expensive means the door is locked, but locks can in principle be picked, and the size of the lock might shrink as you understand it better. Van den Broek turned the warp drive from the first kind of problem into the second kind. He did not make it buildable. He made it the sort of thing you could keep working on without being a crank, and in physics that is a meaningful difference. There was still a deeper objection, though, one that did not care about the size of the number, and it is the objection that will haunt the rest of our story. Many physicists believed, and many still believe, that any faster-than-light warp drive must violate something called the weak energy condition. The weak energy condition is a rule of thumb that all normal, physically reasonable matter seems to obey, a statement that the energy density measured by any observer can never be negative. Ordinary stuff always respects it. And the suspicion, growing into something close to a theorem, was that you simply cannot build a faster-than-light bubble out of matter that respects the weak energy condition. Somewhere in the design, the math insists, you will always need a region where energy goes negative. If that suspicion is correct, then negative energy is not a feature of one particular design that a cleverer design could avoid. It is a tax built into the very idea of moving faster than light. So the warp drive went into its long sleep, and for nearly 30 years that is where it stayed, a beautiful piece of mathematics admired and set aside. Physicists would mention it in popular talks as a charming example of how strange general relativity can be, and then they would add the caveat that of course it could never be built because it needs negative energy in planetary quantities, and that was the end of the conversation. The geometry was never really the problem. The problem was always what you would have to feed it, and what you would have to feed it appeared to be something the universe hands out only in microscopic whispers, if at all. And that is exactly the assumption a new generation of physicists decided to question. Starting around 2021, a handful of researchers looked at that 30-year-old caveat, the flat assertion that warp drives need impossible amounts of negative energy, and they asked a dangerous question. Was it really true? Or had everyone simply been copying the same conclusion from the same original paper without checking whether cleverer geometries might escape it? What happened next is the part of the story that put the warp drive back in the headlines, and it begins with a wave that holds its shape. Is less than break time equals 1s is greater than number. The physicists who reopened the file. In 2021, a physicist named Eric Lentz published a paper that did something the field had quietly assumed was impossible. He proposed a class of warp bubbles that, he argued, could be built from purely positive energy, ordinary energy of the kind that real matter actually carries, with no negative energy debt required at all. The key to his construction was a particular shape, a configuration he described in terms of solitons, and if his analysis held up, it would knock out the single objection that had kept the warp drive locked away for 3 decades. Suddenly, the question was not how to find an impossible substance, but whether a clever enough arrangement of perfectly ordinary energy could do the job. A soliton is worth understanding on its own, because it is a lovely piece of physics, and because it is doing real work in this story. Most waves spread out and fade as they travel. Drop a stone in a pond, and the ripples widen and weaken until they vanish. But under the right conditions, a wave can hold its shape, traveling for great distances as a single, stable pulse that neither spreads nor collapses. Such a wave is called a soliton, and they show up everywhere from canals to optical fibers to the strange physics of certain particles. The first one ever recorded was seen in 1834 by an engineer named John Scott Russell, who watched a single hump of water roll along a Scottish canal for miles without changing shape, and chased it on horseback for a mile or two before it outran him. Lentz's idea was to make the warp bubble itself a kind of soliton, a self-reinforcing wave of curved space that holds its form as it carries the ship along. What made Lentz's proposal land like a small thunderclap was the claim attached to it that this particular wave shape could be generated without any negative energy at all, using only the ordinary positive kind. If that were true, it would have removed the single objection that had defined the warp drive for its entire existence. The reaction in the small community that follows this work was immediate, and it was split. Some saw a genuine breakthrough, the first crack of light under a door that had been sealed for decades. Others were skeptical from the start, suspecting that the negative energy had not been removed so much as hidden, swept into a part of the calculation where it would not show up unless you looked from exactly the right angle. Both reactions, as we will see, turned out to capture something true, and the argument between them is still going on. But even the skeptics agreed that Lentz had done something valuable, which was to force everyone to check, carefully and from scratch, an assumption they had been repeating without checking for 30 years. Around the same time, in the same year, 2 researchers named Alexei Bobrik and Gianni Martiré published a paper with a title that signaled how seriously they were taking all this. They called it Introducing Physical Warp Drives, and their contribution was less a single equation than a complete reframing of the whole subject. Instead of treating Alcubierre's 1994 design as the one and only warp drive, they showed that warp bubbles are an entire family of geometries, a broad class of possible spacetimes that share certain features, of which Alcubierre's was just the first and most famous member. By widening the lens from one design to a whole family, they opened up room to ask which members of the family might be physically reasonable, even if the original was not. Their central result was both encouraging and honest, and the honesty is what makes it trustworthy. They demonstrated that you genuinely can construct legitimate warp shells out of ordinary, positive energy matter, configurations that obey the energy conditions and do not require any exotic substance at all. That was the encouraging part, and it broke the spell that had hung over the field, the assumption that the entire concept was unphysical from the start. But here is the honest limit they were careful to state. The realistic, positive energy warp drives they could actually construct were subluminal. They traveled slower than light. They could carry a passenger smoothly, comfortably, without crushing acceleration, inside a genuine bubble of flat space, but they could not, in their physical form, exceed light speed. You might think a warp drive that cannot beat light is a disappointment, a consolation prize that misses the entire point, but I want to argue that it was actually a profound step forward, and here is why. For 30 years, the objection had not been, you cannot go faster than light with a warp drive. The objection had been, a warp drive is fundamentally unphysical. It needs impossible matter. The whole idea is nonsense. Bobrick and Martier's subluminal drive answered that deeper objection directly. It proved that a warp bubble, a genuine pocket of flat space carried along by reshaped spacetime, is not automatically impossible. It can be built, in principle, from real matter. The concept was sound. What remained in question was only the speed, and speed, as we have seen, is a dial. The field had gone from, is this even physics, to, all right, it is physics. Now how fast can we push it? The reframing Bobrick and Martier offered is worth lingering on, because it changed not just the answer, but the entire shape of the question. Before their work, the warp drive was treated as a single object, Alcubierre's specific design, and you either accepted that one design or you rejected the whole idea. They pointed out that this was like judging all possible bridges by looking at one particular bridge and declaring bridges impossible because that one would fall down. There are, they showed, many ways to arrange space-time so that a flat bubble is carried along inside a shell of curved space, and these arrangements form a whole territory of possibilities, some of them grotesque and unphysical, others surprisingly reasonable. The job of the warp drive physicist, in this new view, was not to defend one sacred equation, but to explore that territory and search for the corners of it that real matter could actually build. It turned a yes or no question into a map to be explored, and maps invite expeditions. In their accounting, a warp drive is really just a clever way of organizing the gravity of a shell of matter so that the inside rides smoothly. The slower-than-light versions can be built from a shell of ordinary mass arranged in a particular way, no stranger in its ingredients than a dense star, and they would still offer some of the warp drive's gentler gifts, the smooth ride, the freedom from crushing acceleration. Even if they could never beat light, that alone would be a revolution in spaceflight if it could be engineered, a way to move without the brutal physics of rockets. But it is not what our title promises, and everyone working on the problem knew it. The subluminal drive was a proof of concept, a planted flag that said, the territory is real, keep digging. The treasure, the faster-than-light bubble without exotic matter, was still somewhere out ahead in that unmapped territory, and the question was whether it existed at all or was only a mirage. The momentum continued. In 2024, the same circle of researchers, working through a group called Applied Physics, published a model they called a constant velocity physical warp drive, a design that could carry a passenger at a steady speed inside a shell of ordinary positive energy matter. Each new paper was another careful step, another piece of the assumption being chipped away, another demonstration that the warp idea could be made more physical than anyone had bothered to check for 3 decades. This was not a field of cranks chasing a fantasy. It was a small, serious research program treating the warp drive as a legitimate open problem and methodically working through it. What I want you to notice about this whole revival is how unglamorous and how real it looks, because this is genuinely how most breakthroughs happen. There was no single eureka, no lone genius shouting in a bathtub. There was a slow erosion of an assumption that everyone had stopped questioning, carried out by several people over several years, each one nudging the number down, or widening the family of possibilities, or answering one more objection. The energy requirement kept shrinking, the geometries kept getting more physical. And crucially, not one of these papers touched Einstein. Every single one of them worked entirely inside general relativity, using the same equations that have passed every test we have ever devised. They were not breaking the rules. They were reading them more carefully, exactly as Alcubierre had. But the subliminal drives, solid as they were becoming, were not what our title promises. The title asks about 10 times the speed of light, and a warp drive that crawls along below light speed, however elegant, is not a way to reach the stars in a human lifetime. The real prize, the faster-than-light bubble built without impossible matter, remained out ahead, unclaimed. And then, in 2025, the papers that genuinely made the news arrived, claiming to have done exactly the thing that mattered most. And that is where the story gets both thrilling and complicated. Is less than break time equals 1s is greater than number the 2025 papers that made the news. In 2025, a physicist named José Rodal published work describing a warp drive spacetime with predominantly positive invariant energy density, a configuration where the energy is mostly positive and the troublesome negative energy regions are dramatically reduced compared to the older designs. The word predominantly is carrying weight there, and we will come back to it, but the direction was clear. The negative energy debt that had defined the warp drive since 1994 was being squeezed smaller and smaller, pushed into thinner and thinner corners of the geometry, as physicists found cleverer ways to arrange the matter that builds the bubble. Then, in November of 2025, came the paper that lit up the headlines, the one that sits directly behind the question in our title. A group of researchers described a superluminal solitonic spacetime, a faster-than-light warp bubble that they claimed possessed positive, semi-definite energy. Read those words carefully, because each one matters. Superluminal means faster than light, the thing the subluminal drives could not do. Solitonic means it uses the self-reinforcing wave shape that holds its form. And positive semi-definite energy is the technical way of saying the energy never has to go negative, that the whole structure can, they argued, be generated from purely positive energy densities. If that holds, it is precisely the combination that 30 years of physicists had said could not exist, a faster-than-light warp drive without exotic matter. The paper also carried a number, and the number is the kind of thing that makes people sit up, so let me give it to you, and then immediately put it in its place. The researchers estimated that the total energy required for their configuration was roughly 4 orders of magnitude smaller than the mass of the Sunday. 4 orders of magnitude means 10,000 times smaller. So instead of needing the energy equivalent of an entire sun, as some of the earliest estimates demanded, this design asked for something like 1/10,000th of that. Set against the history of this problem, where the numbers used to be planetary or stellar and the requirement looked flatly infinite, dropping the bill by a factor of 10,000 is a genuinely dramatic improvement, the kind of progress that turns heads at a conference. And now, the cold water, because this is where being honest matters more than being excited. 1/10,000th of the mass of the Sun is still an absolutely staggering amount of energy. The Sun's mass energy is so enormous that 10,000 times less than it is still comparable to converting a small planet or a very large moon entirely into pure energy with perfect efficiency, and then arranging that energy into an exquisitely precise pattern around your ship. We cannot convert a grain of sand entirely into energy, let alone a moon. So the headline that the energy requirement has dropped dramatically is true, and the reality that the requirement remains wildly, hopelessly, beyond any technology we can imagine is also true. Both things are true at once, and holding them together is the whole skill of reading a result like this correctly. To make the number a little more vivid, consider where that 1/10,000th of a solar mass would have to come from. The most energetic process humanity has ever harnessed, the fusion bombs that frightened the 20th century, converted mere grams of matter into energy, and a few grams was enough to level a city. The sun, by contrast, converts something like 4 million tons of its own mass into energy every single second, and has been doing so for billions of years. When the November paper says its drive needs 10,000 times less than the whole sun's mass energy, it is still naming a quantity that would require converting a body the size of a large asteroid or a small moon entirely and perfectly into energy with no waste, and then holding that energy in an exact configuration around a ship. We have never converted anything entirely into energy. Even our bombs and our reactors release only a tiny fraction of the energy locked in their fuel. So the improvement is genuine, and the destination is still absurd. And both of those facts have to be carried forward together. There is a subtler reason these papers generated excitement beyond the shrinking number, and it has to do with the direction of travel rather than the destination. For 30 years, every serious estimate of the warp drive's cost had said the same discouraging thing, that it was impossible by an infinite margin. Then Van den Broek cut it. Then the positive energy proposals reframed it. Then each new paper trimmed it further. When a quantity that was once described as infinite becomes merely planetary, and then a fraction of a star, and then a fraction of that, the trend itself becomes the headline. Physicists notice trends, because trends sometimes continue. No one can promise that the energy requirement will keep falling until it reaches something achievable, and there may well be a floor below which it cannot go. But the fact that it has fallen so far, so fast, once people started looking, is exactly the kind of thing that pulls bright minds into a problem and keeps them there. A number that only ever moved in one direction would be a dead end. A number that keeps shrinking is an invitation. This is exactly what makes the November 2025 paper the "Have we just found a way" moment that the title points to, and it is also why the phrase "found a way" on paper is doing so much quiet work. What the researchers found, if their analysis is correct, is a mathematical object, a consistent solution of Einstein's equations that describes a faster-than-light bubble built from positive energy. That is a real and significant thing. It is the discovery that the thing we thought was forbidden might not be forbidden after all, at least not by the particular rule everyone assumed forbade it. But a consistent solution on paper is not a buildable machine, and the distance between those two things is the distance between knowing that a mountain can in principle be climbed and actually standing on the summit. I want to give you a tool here, a distinction that will serve you well, not just tonight, but any time you read a breathless headline about a physics breakthrough. There are two completely different senses of the word possible. The first is mathematically allowed, meaning the equations of our best theory permit it. There is no contradiction. You can write down a valid solution. The second is physically sourceable, meaning you could actually assemble it out of matter and energy that genuinely exist and behave the way you need them to. The warp drive has been creeping from the first category toward the second for a few years now, and the 2025 papers are real progress along that path, but it has not arrived. Mathematically allowed is a long, long way from physically sourceable, and the gap between them is where most exciting physics quietly lives and sometimes quietly dies. It is also worth remembering how fresh and how unsettled all of this is, because the speed of the field is part of the story. These are recent papers and preprints, some of them only weeks or months old, being posted, read, and argued over in close to real time. They are not settled textbook physics that has survived decades of scrutiny. They are the leading edge of an active debate, and on the leading edge of any debate, claims get made, then checked, then sometimes overturned, then refined. That is not a flaw in the process. That is the process working exactly as it should. But it means the right posture for us, watching from the outside, is neither breathless belief nor flat dismissal. The honest stance, the one I would encourage you to hold as you drift off tonight, is cautious excitement. Something real is happening in this corner of physics. The energy requirements have fallen by orders of magnitude. The geometries look more physical than they ever have. Serious people are publishing serious math, claiming a faster-than-light bubble without exotic matter. That is genuinely thrilling, and it is not nothing. And at the very same time, it is not a finished answer, not a machine, not a guarantee, and possibly not even correct, because for every paper claiming the negative energy has finally been banished, another paper lands showing that it was only hiding. The dream of 10 times light speed now lives inside equations that look more credible than ever before, and credible is not the same as confirmed. Which brings us to the pushback, and to the two doors that, for all this progress, remain firmly locked. Is less than break time equals 1s is greater than number, the two doors still locked. For every claim that a warp drive can be built from positive energy, there is a team of physicists who take that claim apart, line by line, and report back what they find. And what they keep finding is the negative energy that was supposed to be gone. The most influential of these critiques came from researchers named Santiago, Schuster, and Visser, who examined Lenz's positive energy soliton closely and showed that when you do the accounting properly, when you check the energy density measured by every possible observer rather than just a convenient one, there are still regions where the energy goes negative. The positive energy claim, they argued, was an artifact of looking at the problem from a particular angle. Tilt your point of view, and the negative energy reappears. This critique did not go away. In 2025, a paper titled Violations of the Weak Energy Condition for Lentz Warp Drives continued exactly this line of analysis, arguing that the specific positive energy soliton designs still break the weak energy condition somewhere in their structure, still demand that little forbidden sliver of less than nothing. And it is not only the soliton designs. A verification effort developed around 2026, building a careful toolkit to check warp metrics from every observer's perspective, examined regularized versions of the warp shell models, and found small but real violations of the weak energy condition hiding inside them too. The pattern is hard to ignore. Again and again, a design is announced as free of negative energy, and again, a closer look finds the negative energy tucked into a corner where the first analysis did not think to look. Standing behind much of this skepticism is a physicist named Jose Notario, and his voice matters because he is not an outsider throwing stones. His own earlier work helped refine and clarify the warp drive problem itself, and his considered position is blunt. He argues that genuinely superluminal travel is simply impossible, and that even the subluminal warp drives, the ones widely accepted as physical, still require negative energy somewhere in their construction. When someone who helped build the modern understanding of the problem tells you the faster-than-light versions do not work, that is not a knee-jerk dismissal. That is informed judgment from inside the field, and it deserves real weight in the balance. So, here is the first of the two locked doors, stated as plainly as I can. The negative energy keeps coming back. Every faster-than-light design that has claimed to escape it has, so far, been shown on closer inspection to smuggle it back in. The weak energy condition, that humble rule that all ordinary matter seems to obey, keeps reasserting itself, as if the universe were quietly insisting that you cannot outrun light without paying in a currency that may not exist. The positive energy claims might be real, or they might all turn out to be artifacts of incomplete checking. Right now, tonight, the question is genuinely open, and the weight of expert opinion leans toward the door staying shut. The second locked door has nothing to do with energy at all, and in some ways it is even more stubborn, because no clever geometry seems able to touch it. We met it briefly inside the bubble, and now we face it head-on. The problem is control. Remember that the interior of a faster-than-light bubble is causally cut off from its own leading edge. Signals cannot travel from the front of the bubble back to the ship, and that is not a minor inconvenience. It means the crew, sealed in their flat pocket of space, have no way to steer the bubble or to stop it once it is moving. The very controls that would shape the front wall sit on the far side of a barrier that no signal can cross while the bubble travels faster than light. Picture what that actually implies for a journey, because it is genuinely strange. A warp ship could not be flown the way you fly anything else. It would have to be aimed and timed perfectly before it ever departed. Every detail of the route computed in advance, because once the bubble formed and began to move, no correction would be possible. It is like firing an arrow that you can never adjust after release, except the arrow is carrying your crew across light years, and any error in the original aim cannot be fixed in flight. To stop at the destination, the bubble would somehow have to be switched off at precisely the right instant by a mechanism that the crew, cut off from the leading edge, cannot reach. The deeper trouble with the control problem is that it does not seem to be a flaw in any particular design that a better design could fix. It appears to be woven into the very thing that makes the warp drive work. The same causal disconnection that lets the bubble outrun light, the same severing of the front edge from the interior, is what prevents the crew from reaching the front to steer it. You cannot have one without the other. The feature that grants the impossible speed is identical to the feature that takes away your hands on the wheel. This is a recurring theme in faster-than-light physics, and it is worth naming plainly. The universe seems to defend its limits not with a single lock, but with a kind of cruel symmetry, where every door you pry open swings a second door shut, so that the very mechanism granting your wish quietly cancels the wish in another way. Some physicists have proposed clever workarounds, imagining a string of devices laid out along the route in advance, or a network of smaller bubbles handing the ship off from one to the next, each pre-programmed to fire at its appointed moment. But every such scheme runs into the obvious objection that you would first have to travel the entire route at slower than light speed to set up the equipment, which defeats the entire purpose of having a faster than light drive in the first place. You cannot use the warp drive to build the infrastructure that the warp drive requires. It is a chicken and egg problem written across light years, and no one has found a way out of it that does not quietly assume you already have the very thing you are trying to build. Even if you had the impossible energy and the perfect positive energy geometry, you would still be left with a vehicle that cannot see where it is going and cannot choose when to arrive. Layer on top of those two doors the worries we touched on earlier, the ones about whether the bubble would even survive its own existence. Several analyses suggest the bubble could be unstable, that the delicate arrangement of contracting and expanding space might tear itself apart the moment it tried to exceed light speed. Others suggest the front wall would gather ordinary particles and radiation, concentrate them, blue shift them to enormous energies, and release them in a devastating flash when the bubble stopped, lethal to the crew and to anything waiting at the destination. None of these problems has a clean solution. Each one is the kind of obstacle that stands between an equation that describes a thing and a machine that is that thing. The heating problem, in particular, deserves a closer look because it is one of those quiet details that rarely survives the trip into popular coverage, and it is genuinely chilling. As a warp bubble moves through space, it does not move through perfectly empty space, because no space is perfectly empty. There are stray particles, wandering atoms of hydrogen, the faint background of light left over from the early universe, all of it drifting through the void. As the bubble races forward, these particles can become trapped against its leading wall, unable to pass through, accumulating there like insects on a windshield, except that the windshield is traveling faster than light, and the laws governing that front wall can pump enormous energy into whatever it catches. By the time the bubble reached its destination and switched off, releasing everything it had gathered, the result could be a forward-directed blast of radiation so intense that it would sterilize whatever lay ahead. The warp ship would arrive at its target star not as a gentle visitor, but as a weapon that had been unknowingly charging the entire journey, and the crew, sealed behind that wall, might not survive the stopping any more than the destination would. That detail changes the emotional texture of the whole dream, and it is worth letting it. We began with the gentlest image imaginable, a passenger floating calm and weightless, while the galaxy slides past the window, and we have arrived at the possibility that the same vehicle is silently accumulating a lethal charge with every light year, blind to the danger, because it cannot see its own front edge. The warp drive keeps doing this, offering a beautiful gift with one hand and revealing a hidden cost with the other. And that pattern, more than any single objection, is what makes it such a hard thing to either embrace or dismiss. If I gather all of this into a single fair verdict, it goes like this. The subluminal warp geometries, the ones that travel slower than light, stand on increasingly firm ground, and they are genuine, respectable physics that may even point toward exotic but real possibilities someday. But the faster-than-light versions, the ones our title is actually about, the ones that promise 10 times light speed and 5 months to another star, still trip the same 2 wires every time. There is negative energy that refuses to disappear, and there is a bubble that cannot be steered or stopped. The Have We Found a Way of our title runs straight into these 2 locked doors, and as of tonight, neither one has opened. And yet, even granting all of that, the warp drive remains the most credible, faster-than-light idea we have. And that is not because it is easy, but because the alternatives are worse. If we genuinely want to beat the speed of light, the warp drive is one of only a handful of famous candidates. And to understand why so much hope rests on this difficult, locked-up idea, we need to look at its rivals and watch each of them fall. Is less than break time equals 1s, is greater than number. The other shortcuts, and why they fail. If you wanted to beat the speed of light and someone handed you a list of every serious idea physics has ever entertained, that list would be short, and the warp drive would be only one entry on it. To understand why so many thoughtful people keep coming back to the warp drive, despite its 2 locked doors, it helps to walk down the rest of the list and watch what happens to each rival when you press on it. There are really only 3 other famous candidates, and each one fails in its own instructive way, and the manner of their failure tells us something important about why the warp drive, for all its difficulty, keeps surviving. The first rival is the wormhole, and it is probably the one you have seen most often in films. The tunnel that folds 2 distant places together so you can step through one mouth and emerge from the other halfway across the galaxy. The wormhole is not science fiction in its origins. It is a legitimate solution of general relativity, first described in connection with Einstein himself, sometimes called an Einstein-Rosen bridge. The mathematics genuinely permits a tunnel through space-time, a shortcut that connects 2 far-apart points directly so that the long way around through ordinary space could be bypassed entirely. On paper, the wormhole is real physics, and that is exactly why it gets taken seriously. But press on the wormhole, and the same villain we have been chasing all night steps out of the shadows. To hold a wormhole open, to keep its throat from pinching shut the instant anything tried to pass through, you need exotic matter, matter with negative energy, threaded through the tunnel to prop it open against its own tendency to collapse. It is the very same negative energy that the warp drive cannot escape, the same forbidden currency, the same weak energy condition standing in the way. And on top of that, no wormhole has ever been observed anywhere in the universe. We have no evidence that a single one exists, no hint of a natural example, nothing but the mathematical possibility and the same impossible ingredient. The wormhole does not solve the negative energy problem. It simply relocates it from the wall of a bubble to the throat of a tunnel. The wormhole has one additional problem that the warp drive does not share, and it makes the tunnel even less appealing as a practical route. Even if you could somehow find or build a wormhole and prop it open with exotic matter, you would only be able to travel between the two specific points where its mouths happen to be. A wormhole is not a general-purpose vehicle you can aim wherever you like. It is a fixed shortcut between two fixed locations, and to reach a new destination, you would need a new wormhole, with both mouths somehow placed at the points you cared about, which raises the question of how the far mouth got to the far star in the first place without faster-than-light travel to carry it there. The wormhole, like the warp drive's pre-programmed route, tends to assume the very capability it is supposed to provide. The warp drive, for all its faults, at least promises a ship you could in principle point at any star you chose. The second rival is more exotic still, a hypothetical particle called the tachyon. The idea is elegant in its way. Special relativity forbids accelerating a normal particle up through the speed of light, because of that infinite wall of energy we discussed. But what if there were a particle that was born on the other side of the wall, a particle that always travelled faster than light and could never be slowed down to light speed, just as ordinary matter can never be sped up to it? Such a particle would live permanently in the faster-than-light realm, and physicists gave it the name tachyon, from the Greek word for swift. For a while, it was a serious topic of investigation, a what-if worth chasing. There is a quieter fourth idea that sometimes joins this list, called the Krasnikov tube, and it is worth a mention because it shows how the same villain keeps reappearing under new names. The idea is to leave a permanent corridor of modified space-time behind a ship as it travels outward at near light speed. A tube that reshapes the relationship between space and time along the route so that the return journey back through the tube could be made in almost no time at all. It solves one problem the warp drive cannot, the steering problem, because the corridor is laid down deliberately as you go, but it pays for that solution in the same currency as all the others. Building and holding the tube open requires exotic matter with negative energy, the identical forbidden ingredient, and the outbound trip must still be made the slow way before any shortcut exists at all. The Krasnikov tube is less a rival than a cousin, another arrangement of the same loophole, tripping over the same threshold. The tachyon fails for two reasons, and the second is far more damaging than the first. The first reason is simply that we have never detected one. Despite searches, no tachyon has ever shown up in any experiment, and most physicists now regard them as a mathematical curiosity rather than a real feature of nature. But the second reason is the one that truly buries the idea, and it is a reason we are going to meet again at the very end of our journey. If tachyons existed and could carry signals, then you could use them to send messages faster than light, and a faster-than-light message, when you work through the relativity of it carefully, can be arranged to arrive before it was sent. You could, in principle, send information into your own past. That shreds the relationship between cause and effect, the basic principle that causes come before their consequences, and physics treats the breaking of cause and effect as very nearly the deepest sin a theory can commit. The third rival is the one that fools the most people, because it is completely real and yet promises nothing it can deliver. It is quantum entanglement, the phenomenon Einstein himself called spooky action at a distance. When two particles become entangled, Their properties are linked in a way that survives any distance between them. Measure one particle, and you instantly know something about its partner, whether that partner is in the next room or on the far side of the galaxy. The correlation is genuine. It has been confirmed in thousands of careful experiments, and it appears to be instantaneous, with no signal traveling between the two particles at all. Surely, people think, here at last is faster-than-light communication, ready-made and proven. It is not, and the reason why is one of the most beautiful guardrails the universe has ever built. It is called the no communication theorem, and it proves, rigorously, that you cannot use entanglement to send a usable message faster than light. The catch is that the result of measuring your particle is random. You cannot choose what answer you get, and so you cannot encode a message into it. When you measure your particle and instantly learn about its partner, you have learned a correlation, but you have not sent anything. For the person on the other end to know that anything meaningful happened, you have to tell them what you measured, and that telling, that comparison, can only travel by an ordinary signal at or below the speed of light. Entanglement gives you a shared secret, but it cannot carry a payload. It is faster-than-light correlation with no faster-than-light communication, the universe handing you something that looks like a loophole and turns out to be sealed. People often point to a phenomenon called quantum teleportation as a counterexample, and it is worth clearing up because the name promises something the physics does not deliver. Quantum teleportation is real, and it does transfer the exact state of one particle onto another distant particle, which sounds like exactly the faster-than-light trick we are after. But buried in the procedure is a step that ruins the dream. To complete the teleportation, you must send a small amount of ordinary information from one end to the other, a couple of bits describing a measurement, and that information can only travel by a normal channel at or below the speed of light. Until those bits arrive, the distant particle holds no usable copy of anything. The teleportation is only finished when the slow message catches up. So even this, the most science fiction sounding piece of real quantum physics, politely tips its hat to the speed limit and waits for the slow signal before it will do its trick. Once again, the universe lets you peek through the keyhole and then closes the door before you can step through. Step back and a pattern emerges that is almost too neat to be accidental. Every shortcut that does not move space itself either requires the same forbidden negative energy, or breaks the sacred rule of cause and effect, or carries no usable information at all. The universe seems to have anticipated every clever route a determined species might try, and posted a guard at each one. Only the warp drive, by refusing to send anything through space and instead moving the space, manages to dodge 2 of the 3 guards outright. It carries a real ship with real cargo, unlike entanglement. It does not, by its basic operation, require a new undetected particle, unlike the tachyon. Its remaining problems, the negative energy and the threat to causality, are the 2 guards no one has gotten past, but it is the only candidate that even reaches them with most of its dignity intact. So look at what the list has done to itself. Wormholes need the same exotic negative energy the warp drive needs, and have never been seen. Tachyons have never been detected, and would shatter cause and effect if they existed. Entanglement is real and proven, and utterly unable to send a message. 3 rivals, 3 failures, each one either demanding the same forbidden ingredient, breaking the same sacred principle of causality, or carrying nothing at all. And against that field of collapse, the warp drive stands oddly tall because of everything it does not require. It does not need a new undetected particle. It does not by itself send a signal into the past. It keeps the ship sitting in perfectly ordinary, legal, local physics the entire time, obeying every rule in its own little region while the space around it does the moving. Notice, too, the shared villain that has stalked nearly every idea tonight, because it is telling us something. Wormholes need negative energy. The warp drive keeps needing negative energy. Tachyons and faster-than-light signals threaten causality, and so, lurking at the edges, does any genuine faster-than-light travel. Over and over, the routes to beating light collide with the same two obstacles, negative energy and broken cause and effect, as though the universe had posted two guards at the only two gates and told them to turn everyone away. It is almost as if these are not separate problems at all, but two faces of a single profound resistance the cosmos puts up against anything outrunning light. That repetition is itself a clue, and some physicists take it as more than coincidence. When the same two obstacles, negative energy and broken causality, block every road you try, it begins to look less like a string of separate engineering difficulties and more like a single underlying principle wearing different masks. Perhaps the universe is not forbidding faster-than-light travel by a dozen unrelated rules that we keep bumping into one at a time. Perhaps there is one rule, stated in different languages depending on which route you take, and that one rule is something like this: you may not arrange the universe so that an effect comes before its cause. Negative energy may be forbidden in the quantities a warp drive needs precisely because allowing it would let you break causality. The two guards at the two gates may, in the end, be the same guard. If that is true, then the warp drive's hardest problem is not the energy or the steering at all. It is that the universe protects the order of time, the way a living thing protects its own pulse, and faster-than-light travel, by any road, eventually asks it to skip a beat. And this is exactly why the elimination matters, why walking down the list was worth our time. The warp drive is interesting, not because it is easy, but because it is the last candidate standing. By knocking out the wormhole and the tachyon and the entanglement shortcut, we are left with the one idea that does not ask us to break Einstein, only to persuade space itself to carry us, the way the expanding universe carries galaxies apart, without any of them breaking the law. That is the whole reason the new positive energy papers carry such weight. In a field where every rival collapses, any genuine progress on the one survivor is news. The warp drive earns its place at the front of the line not by being unproblematic, but by being the only shortcut whose problems might, conceivably, someday, be solved without rewriting the foundations of physics. It is the loophole that does not require a crime, only an engineering feat of impossible scale, and impossible scale, history suggests, has a way of slowly becoming merely difficult. I do not want to oversell that last thought, because the history of technology is also littered with things that stayed impossible no matter how long we worked at them, and the warp drive may well be one of those. But it is worth remembering how often the word impossible has turned out to mean only not yet, especially when the obstacle was scale rather than principle. Heavier-than-air flight was declared impossible by serious people within a few years of the first airplane. Splitting the atom was called moonshine by the very physicist who first described the nucleus. The difference, and it is a crucial one, is that those things violated no law of nature. They only exceeded the engineering of their day. The honest question about the warp drive is which kind of impossible it is. If the negative energy is a true prohibition written into the laws, then no amount of cleverness will ever build it, and we should make our peace with the speed of light as a permanent wall. But if the negative energy is merely very hard to gather, an engineering problem rather than a law, then the shrinking numbers of the last few years are exactly what the early days of a slow conquest look like. We do not yet know which story we are in, and that uncertainty is the most exciting and the most frustrating thing about the whole question. Is less than break time equals 1s is greater than. Number the hype graveyard. Before we reach the end, honesty requires a detour through a graveyard, because the road to faster-than-light travel is littered with breakthroughs that turned out to be nothing at all, and you deserve the tools to tell the real papers from the press releases. The history of exotic propulsion is full of announcements that thrilled the public and then quietly evaporated under careful examination, and knowing this pattern is the best protection against being fooled by the next one. The clearest example is a device called the M-Drive, which promised something that sounded too good to be true and turned out to be exactly that. Its inventors claimed it could produce thrust without expelling any propellant, pushing a spacecraft forward with nothing but microwaves bouncing inside a sealed cavity, in apparent defiance of the basic law that says every push requires something pushed against. For a few years it generated breathless coverage and even some tentative laboratory measurements that seemed to show a tiny force. But when careful, independent teams tested it properly, most notably a group in Dresden around 2021, the thrust vanished. What had looked like a revolutionary force turned out to be the experiment heating up and interacting with the Earth's magnetic field and the test equipment itself. The M-Drive did not break the laws of motion. The early measurements had simply been fooled by subtle effects, and once those were controlled for, there was nothing left. A second example sits closer to our actual subject and is more cautionary, precisely because it touched the warp drive directly. Around 2021, a team associated with a NASA laboratory announced that, while running experiments on tiny Casimir cavities, they had accidentally produced a nanoscale warp bubble, a microscopic region that supposedly matched the structure Alcubierre had described. The headlines wrote themselves. NASA detects warp bubble. The future is here. But the wider physics community did not accept the interpretation. What the experiment had found was a particular energy distribution in a small cavity, and the leap from that to here is a warp bubble was an interpretive stretch that most physicists found unconvincing. It was not a fabrication, but it was an overclaim, a modest result dressed in the language of a revolution. The story spread far faster than the correction that followed, which is the usual fate of an exciting claim and a quiet retraction. And for a while, a great many people believed humanity had built a tiny warp bubble in a lab. It had not. This is worth remembering, not to make anyone feel foolish, but because it is exactly the kind of confusion that makes a calm, careful look at the real papers so valuable. The same words, warp bubble, can describe a genuine and difficult piece of theoretical physics or a wildly overstated laboratory result, and the only way to tell them apart is to ask the boring, essential questions. Has it been published where others can check it? Have critics been allowed to attack it? Did it survive? The exciting answer and the trustworthy answer are not always the same, and learning to prefer the trustworthy one is the whole difference between following science and following headlines. The lesson of the graveyard is not that all such claims are frauds, because they usually are not. The lesson is that extraordinary propulsion claims have a long and consistent history of evaporating the moment they meet rigorous, independent scrutiny, and that the gap between an exciting measurement and a confirmed breakthrough is where most of them die. So here is the tool I promised you, the thing that separates the recent warp papers from the contents of this graveyard. The difference is peer review, published mathematics that anyone can check, and open argument among experts who are actively trying to prove each other wrong. The 2025 warp papers are not press releases announcing a working device. They are calculations, posted openly, immediately challenged by other physicists, refined and contested in public. That process, the constant adversarial checking we saw in the previous part, is exactly what the M-Drive and the warp bubble announcement could not survive. A press release asks you to believe. A published calculation invites you to find the error and hands you everything you need to do it. When a warp paper appears, and 3 other groups immediately publish responses, pointing out where the negative energy is hiding, that is not the system failing. That is the system working, the immune response of science attacking a claim to see whether it is strong enough to survive. The M drive had no such math to attack, only a measured wisp of thrust that vanished under better measurement. The warp papers have equations that critics can and do tear into, and so far the equations keep generating more equations, more responses, more refinements. The argument itself is the evidence that something real is being discussed, even when the conclusion is that the door remains shut. The warp drive is worth taking seriously precisely because it keeps surviving the scrutiny that sank the others, even as that same scrutiny keeps its two doors firmly locked. Is less than break time equals 1s, is greater than number 5 months to another star. Let us finally pay off the number we started with, because now you have earned the full meaning of it. At 10 times the speed of light, the nearest star beyond our Sun, Proxima Centauri, lying about 4¼ light years away, would be reachable in roughly 5 months. 5 months. A single voyage, shorter than a pregnancy, to another sun, that is the entire seduction of our title compressed into one figure. The promise that the unreachable could become a season's journey, that a human being could leave Earth and stand in the light of another star and come home with the story. Now, feel the weight of how far that is from where we actually stand. Our fastest spacecraft, Voyager 1, launched in 1977 and still flying outward after nearly 50 years, is the most distant object human hands have ever made. And if Voyager 1 were aimed at Proxima Centauri, travelling at its real speed of about 17 kilometers every second, it would take something like 75,000 years to arrive. 75,000 years against 5 months. That is the chasm between the dream and the engine, between what the warp drive promises and what our rockets can actually do. The entire recorded history of human civilization is shorter than the time it would take our best machine to reach the nearest star. And yet, even the dream has its humbling limit, and I want to give you this one to keep you honest with yourself as you drift off. Suppose we had it. Suppose the impossible energy and the perfect positive energy geometry and a way to steer and stop the bubble, all of it solved, 10 times light speed in hand. Our galaxy, the Milky Way, is about 100,000 light years across. At 10 times light speed, crossing it from one edge to the other would still take about 10,000 years. The galaxy is so enormous that even outrunning light by a factor of 10 leaves you crawling across it for 100 human lifetimes. 10 times light speed, the number that sounds like the conquest of distance itself, barely dents the scale of the thing we live inside. The universe humbles every speed we can dream of. It is worth holding both of those numbers in mind at once, because together they capture the strange place the warp drive occupies in our imagination. 5 months to the nearest star is close enough to taste, a journey a single human being could make and return from, the kind of trip that would turn interstellar travel from an abstraction into an experience. 10,000 years to cross the galaxy is so long that it dwarfs all of human history many times over, a reminder that even our most extravagant dream of speed is a small thing against the scale of what is out there. The warp drive, if it ever existed, would not make the universe small. It would only make our own immediate cosmic neighborhood, the handful of nearest stars, reachable within a lifetime, while leaving the galaxy as a whole as enormous and as patient and as far beyond us as it has always been. That is not a disappointment. It is a correction to the fantasy, a reminder that the prize, even fully won, would be a few neighboring suns, not the conquest of infinity. And there is a quiet dignity in that smaller dream if you let yourself feel it. To reach even one other star, to stand a human being in the light of a sun that is not our own and bring them home again, would be the greatest thing our species has ever done, and it would not require conquering the whole universe to mean everything. The warp drive does not have to deliver the galaxy to justify the longing behind it. It only has to deliver the next star, and that, against the 75,000 years our rockets demand, would be miracle enough. There is one more shadow to name before we close, the deepest of them all, the one that makes physicists most uneasy about every idea we have discussed tonight. It is the problem of causality. Any genuine way to travel or signal faster than light can, when you combine it carefully with the relativity of time between moving observers, be turned into a way of sending information into the past, of arranging for an effect to occur before its cause. That is not a minor technicality. The principle that causes come before effects may be the single most fundamental thing we believe about the universe, more fundamental even than the speed of light, and any faster-than-light scheme, warp drives included, has to find some way to avoid letting you murder your own grandfather before you were born. This, more than the energy, more than the steering, is the real reason so many physicists distrust the whole enterprise. It is not just hard to build. It threatens the order of cause and effect on which everything else rests. Let me make the causality problem concrete, because in the abstract it sounds like a technicality, and in the concrete it sounds like a nightmare. Suppose you had two warp ships, and suppose, as relativity insists, that there is no single universal clock, no master time that everyone agrees on, only the time measured by each observer in their own frame of motion. With faster-than-light travel available, you can arrange a sequence of trips between moving observers, such that a message, or a traveller, arrives back at the starting point before the moment of departure. Not metaphorically, literally. You could, in principle, send a signal that reaches your past self, who could then choose to prevent the signal from ever being sent. The chain of cause and effect, the simple fact that the cause comes first and the effect follows, would be broken, and once it is broken, the universe stops making the kind of sense that lets us reason about anything at all. This is sometimes called the grandfather problem, and it is not a quirk of one particular scheme. It haunts every method of beating light, the warp drive included, the moment you take relativity seriously. Physicists have a few uneasy responses to this, none of them fully satisfying. Some suspect that nature simply forbids faster-than-light travel precisely in order to protect causality, that the negative energy requirement and the other obstacles are not separate problems, but the universe's way of slamming this deepest door shut. Others speculate that if faster-than-light travel were possible, the universe would somehow conspire to prevent the paradoxes, that events would always arrange themselves so that you could never actually change the past, only ever take part in what already happened. And a few are willing to entertain the wildest possibility that travel into the past would spawn new branches of reality rather than altering our own. We do not know which, if any, of these is right. But the fact that a working warp drive would force us to confront this question at all is, to many physicists, reason enough to suspect the door will stay closed. So what is the honest answer to the question in our title? Have we just found a way to travel 10 times faster than light? On paper, in fresh and serious mathematics published in the last few years, the door looks less bolted than it did a decade ago. The energy requirements have fallen by orders of magnitude. The geometries look more physical than ever, and at least one 2025 paper claims a faster-than-light bubble built from positive energy alone. That is real, and it is remarkable. But no one has yet shown a faster-than-light drive that does not, on closer inspection, still demand negative energy that may not exist, and no one has solved the problem of a bubble that cannot be steered or stopped. And no one has answered the threat to cause and effect. The way has not been found. What has been found is that the search is not foolish, that it belongs in journals and not only in fiction. Maybe the truest way to put it is this: have we found a way is the wrong tense for the question. The way is being searched for, openly, by real physicists, with the impossible numbers shrinking decade by decade and the impossible geometries growing more plausible paper by paper. It is not a moment of discovery. It is a slow, patient excavation, and we are somewhere in the middle of it, with no way to know whether the tunnel ends in open sky or solid rock. The people doing this work will likely not live to see the answer, and neither, in all honesty, will we. That is the strange humility of a problem this size. You take up a tool, you move the question forward by one small, careful step. You hand it to whoever comes next, and you trust that the answer, whatever it turns out to be, is worth the centuries it may take to reach. There is a kind of faith in that, not the faith that we will succeed, but the faith that the question is worth asking, even if the answer arrives long after everyone now alive has gone quiet. The universe wrote the loophole into its own laws. It demonstrates that loophole across the entire sky, every single night, in the receding of distant galaxies, and in the memory of that first faster-than-light instant of creation. The cosmos clearly knows how to move space faster than light. The only question is whether we can ever learn to do on purpose, in a tidy bubble of our own making, what the universe does for free across all of existence. And here is the thought I will leave you with as you settle deeper into the quiet. The most haunting possibility in all of this is not that faster-than-light travel turns out to be impossible. We could make peace with impossible. The most haunting possibility is that it is allowed, that the universe left this door unlocked in the fine print of its own laws, written it into the same equations that govern the falling of an apple and the orbit of the moon, and that the only thing standing between us and the stars is whether we are clever enough, and patient enough, and lucky enough to find the key that we already know exists. A universe that may be reachable in principle and unreachable in practice is a strange and lonely place to be born into, a house full of rooms we can see through the windows and may never walk into. And whether that gap is a permanent wall or merely a problem not yet solved is, perhaps, the most important thing we do not yet know about our place in everything there is.